Welcome, everyone, on the second day of conference. I hope that you had a really good day yesterday and that you are ready to learn new things, starting from Solid in architecture. When we think about software architecture, we can think about two values that this architecture has. The first value is behavior. Basically, it means whether our application fulfills business requirements or not, whether it works or not. In other words, whether it makes money for us or saves money for us. This is strictly product value. The second value is architecture. And this value differentiates software from hardware. And we are all writing software here. So by definition, it should be easy to change. And architecture tells whether this change will be easy or not, because requirements will change. And if we will have bad architecture, this change will take us a lot of money and time. One may ask which value is more important, but I think that those two values should be equally important for us, unless we don't care about product, and we should. But Uncle Bob's, in his books, gives us a really nice example. Let's imagine that we have application that works. It makes money for us, but the architecture is really bad. And market suddenly changed, OK? So we are not able to adapt to those changes before our competitors. And suddenly we are out of the market. But imagine that you came to you have new job, or you came to the new project, and you have project with good architecture, but it has a bug, and it doesn't work. Okay? So with good architecture, you can fix this bug in no time, and when market change, you can adapt to those changes also in no time before your competitors. This is why we should care about architecture at our everyday work. My name is Michal Ksionek. I'm backend developer at DocPlanner in Warsaw. And DocPlanner is a web platform where you can find a doctor and book a visit. We operate on those countries that you can see on the map. Besides this web platform, we also have some kind of back office application for doctors, where they can manage their calendars, their patients, etc. But enough about me and DocPlanner. Let's talk about Solid. I hope that everyone knows what Solid is. Well, basically, Solid, those are 5 principles that tells us how to write good code, how to write methods, how to write classes, how to connect those classes with each other. But what about architecture? Maybe you are writing some microservice, or maybe you want to write some library or some component, or maybe you are writing modularized monolith. And you are wondering how to gather classes into this module, how to decide which classes should go to which component, which class should go to which module, or so on. So how to decide about this situation? It appears that in architecture, we also have some guides, principles that will tell us about it. I mentioned that about components. Basically, architecture consists of components. Okay? This is like the collection of components. But what components are? Components, basically by definition, are units of deployment. And in many different languages, those can be different things. In Java, it could be jar files. In Ruby, those can be gem files, or DLLs in C#. In compiled languages, they can be linked together into a single executable, or aggregated into a single archive. Or they can be independently deployed as plugins. But the most important thing in components is that they are independent. They should be independently developable. So how to build those components? When we want to build components, we can talk about component cohesion. And there are 3 rules that will tell us about component cohesion, how to decide which classes should go to which components. The first rule is the reuse-release equivalence principle. And according to definition, it tells us that the granule of reuse is the granule of release, and that the unit of reuse is the unit of release. And basically, it tells us that components are tracked through a release process, and they are given a release number. And classes and modules gathered into a single component should be released together. So this fact tells us, this fact that they are released together and that they have common release number, tells us that they should have common theme, common goal, common functionality. Though it's very weak definition, but it's hard to make it more explicit. And because component is collection of classes, this cannot be random collection of classes. Those classes should be somehow linked together, okay? And when we fail with this principle, it will be clearly seen by our users. If we will force user to upgrade their component version because of the change that we made that is completely not related with the functionality of a component, they won't be really happy. Also, this principle helps us keeping our components compatible. And the second rule that tells us about component cohesion is common closure principle. It tells us that we should gather into component those classes that change for the same reasons and at the same times. And this may sound familiar, because this is SRP in terms of architecture. This is very similar to single responsibility principle. If 2 classes are so tightly bound, conceptually or physically, they should belong in the same component. This rule is also very closely associated with, it's very closely associated with open-close principle. Open-close principle tells us that we should design our classes in that way that they are close to the common kind of changes that we can expect. So common closure principle amplifies this principle and tells us that we should gather together those classes into a single component. So when unexpected change will happen, there is high probability that we will have to implement this change in minimal number of components. The third rule that tells us about component cohesion is the common reuse principle. And it tells us that we shouldn't force user of a component to depend on things that they don't need. Well, classes are not used seldom, okay? One class to work needs other classes. They don't work in isolation. So if 2 classes are so strongly related with each other, they cannot work without each other. They are inseparable, and they should be in the same component. And this rule, this principle, is a strong analogy to interface segregation principle. And let's imagine that we have a component that has 100 classes, okay? And 2 classes out of this 100 are completely not related with the other 98. And imagine that we made a change. Well, if we depend on this component, it doesn't mean that this dependency is weaker. The dependency is still there. So if we will have change in one of these 98 classes, we will have to check if our code didn't break when we use this component, OK? And if we have separate classes, they should belong in other component. You may notice that REP and CCP are inclusive principles. They will make our components larger. And CRP is more exclusive principle. It will rather try to make our components smaller. So how to decide which principle we should use in our project? Uncle Bob gives us a so-called tension diagram, which tells us what happens if we will use one principle more than other. On the edges of this diagram, we have consequences of abandoning principle on the opposite vertex. So for example, if we will focus more on REP and CRP, we will have a lot of small components. And if we will have to change something in our application, then we will probably have to introduce this change in a higher number of components. On the other hand, if we will focus on CCP and REP, so we will have larger components, then we will have to release this component very often with every change. It's very important that we should find a position on this tension diagram that fits to our current situation. And current here is a very crucial word, because this position is not fixed. Okay? So at the beginning of every project, we'll probably like to be somewhere on the right-hand side of this diagram, because developability is more important than reuse. But if the project matures, it becomes larger, we will probably want to have more smaller components that we want to use in different parts of our application. Then we will slide toward left. So we already know how to build components. We have some guides. But how to connect those components and make them work together? We also have 3 rules that tells us about component coupling. The first rule is the acyclic dependency principle. It basically tells us that we shouldn't allow cycles in the component dependency graph, and it tells about managing the dependency structure of components. And it's easy to explain it on some example, abstract example. Let's imagine that this is the dependency graph for some application. Okay? It doesn't matter what this application does. We have very clear situation here, because if we will make change in component B, then we have to check if we didn't break component A. If we make change in component A, we have to check, well, nothing, because no other component depends on component A. In compiled languages, when we want to build and test our application, we will want to build and test starting from the components at the very bottom of dependency graph. So here we would have to test and build component E, then component BC, then component D, and at the end, component A. So let's imagine that new developer came to our team, and he said that he needs to introduce dependency in component E on component D. Okay? So in this situation, from component B point of view, we no longer depend on small component E. We depend on larger component CDE, because now component E is also dependent on component D. But this is not the worst thing. The worst thing is when we have to build and test this application, because there is no way to say which component is at the very bottom of the dependency graph. We have cycle, and we don't have directed acyclic graph anymore. So how to fix this situation? We should break the cycle. And the easiest thing to break the cycle is to use dependency inversion principle. Because if we have dependency between two components, A and B, and we want to inverse this dependency, we can introduce interface to component B in component A and implement this interface in component B. This way we will break the cycle. But we can do other thing, which is extract classes from component E and from component D and create new component from those classes. And this tells us a very important thing, that we cannot design our architecture at the beginning of our project. The architecture is volatile. It will change with time. It will change with our project. And we should constantly monitor our architecture, detect the cycles, and break them if there is such need. The second principle is the stable dependencies principle. It tells us that we should depend in the direction of stability. But what stability is? According to dictionary, stability is, Stability is an amount of work needed to change something. And as we previously said, we are writing software, so we expect that some components should change. They will change. They are designed to be volatile. So stable component is a component that needs a lot of effort to make a change in this component. Component number one has at least 3 reasons not to change, because 3 other components depend on the component 1. An unstable component is a component that change in this component is relatively easy. So here, component 1, if we want to change component 1, we don't have to do anything else. So the change is very easy. We can measure instability of components using this very complex formula, where fan-out is outgoing dependencies. This is the number of classes outside our component that are using our component. And fan-in, this is number of incoming dependencies. So this is the number of classes inside our component that are used by other components. Instability can have value from 0 to 1, where 0 means that we have as stable component as it can be. So it doesn't have outgoing dependencies, but other component depends on this component. So changing in this component can be really hard. And instability equals 1 means that we have very unstable component. So no other component depends on our component. And we can change this component easily. Depend in the direction of stability. That means that if we want to introduce dependency on other component, we have to be sure that instability of component that we want to depend on is lower than our component. But again, let's imagine that we have a new guy in the team, and he wrote a component that we know that we will change this component very often. And he decided that he needs a dependency in component 1 from this flexible component. Okay? So now we have a situation where we want to change very often component flexible, but it's dependent on the stable component number 1. So if we break component number 1, we will have to change component number 1, and we know that it will take us a lot of effort. But again, we can fix this situation by using dependency inversion principle. We can introduce interface between those two components and make a component just from the interface. This is common practice in compiled languages like Java or C#, and probably we won't see this very often in PHP. The third principle is the stable abstraction principle. And it tells us that component should be as abstract as it is stable. It helps us to define where we should put our high-level policies versus our concrete implementations of those policies. Okay? We know that high-level policies doesn't change very often. So probably we would like to put them into stable components. But some parts are going to be changed. So those should be put in components unstable. But how to create components that are flexible enough to be extended without modification? How to create classes that are flexible enough to be extended without modification? And the answer lies in open-close principles. Those are abstract classes. So according to the stable abstraction principle, which tells us about the relationship between stability and abstractness, stable component should be abstract, and unstable component should be concrete. But with classes, it was relatively easy, because class can be abstract or final in period. But component as a collection of classes can be partially stable and partially abstract. And again, we can measure abstractness using, again, very complex formula, where NA is the number of abstract classes and interfaces in our component, and NC is the number of classes in total in our component. So when we will take instability from the previous rule and abstractness from this rule, we can make a chart like this one, if it works. Yeah. No. Sorry, again, something wrong with my pilot. Here. We can create a chart like this one for our application. What we can notice here, we have two sweet spots that we would like to see our components. And I don't know if it will be. No, we cannot see. OK. So on the left upper corner, we have a green circle. And this is unstable component, which is very concrete. So this is our first spot. And the second sweet spot is on the right lower corner, with abstraction equals 1 and instability equals 0. This is a very abstract component that is very stable. And we can define also two zones on this chart. The first zone is on the upper right corner. Fortunately, we don't have any components there. Those components are abstract and very unstable. Because they are very unstable, that means that probably no other components depend on this component. And because it's abstract, it probably doesn't work. So those components may be some kind of leftovers after refactors, or some leftovers after some legacy code. And we can probably remove those components and delete them. On the other hand, we have lower left corner, which is so-called zone of pain. Because those are very stable components, so we have a lot of dependencies to this component. And those are very concrete components. Those are very concrete implementations. And if they are concrete, there is high probability that we will want to change something in those components. And because they are stable, this change will cost us a lot of effort. So probably we would like to refactor those components to get as close as possible to the green line on this chart. Unfortunately, we will have some components that will lie in this zone of pain, and we can't do anything about it. For example, database schema is such component. We make a lot of changes in database schema, and it's very concrete implementation. This graph was generated by pdepend, but there are also other static analysis tools that you can use to make similar charts, that you can use to monitor your architecture. They will calculate for you instability, abstractness, and some other indicators for architecture. I highly encourage you to think about architecture when you are building your projects. And I highly recommend you to read Clean Architecture, written by Robert Martin. He describes all those rules in more detailed way. Thank you very much.